the fundamental theorem of calculus, and there's, like I said, there's two parts to it. This is really the breakthrough that the two guys that we credit with the invention of calculus discovered. A lot of the methods that we've done so far with calculus, with taking derivatives, with taking integrals, those things were already known. What was not known was the connection between them, and that's what the fundamental theorem of calculus describes and formalizes. There are two parts to it, and we'll kind of see how the two parts are related to each other here as we go. The first part looks a little bit crazy. So here's what it says, and you don't need to write it down. It's in the book. If you're the kind of person that remembers things better when you write it down, feel free, but I don't know if it's really going to help you that much. If you are going to write something down, this part down here at the bottom, this is what you really need to know. So what it says is if we have a continuous function on some interval, and capital F of x is defined as the integral from any constant to the variable x of the function with respect to time integrated with respect to time, then that function, the big F function, has a derivative at every point, and the derivative of f is equal to the derivative of this integral, which is equal to the function itself. I know, right? That's, like I said, it's a little bit crazy, and it's a lot to take in at one time. Here's what's going on. And I'm going to oversimplify this to start with. What we have here is we have a function defined as the integral of another function. So the integral, and this is a definite integral from a to some x, the integral of little f is big F. Okay, so big F is a function that's defined as the integral of little f. The derivative of the integral, so the derivative of big F, is little f. Okay, so here's what it's saying. The derivative of the integral is the original function, which says that the derivative and the integral are what? Opposite. They're inverses of each other. So if we take the integral of a function, and then we take the derivative of it, we get back to where we started. And that's what this is essentially saying. An oversimplified version of it, at least. Alex's question is, how do you have a function that's equal to an area? More specifically, and I think this is what you're asking here, how do you have a function that's equal to an area where a definite integral is just a number, right? So if the function is just a number, why wouldn't it just be f of x equals pi or 10 or whatever the area is? And the reason it's a function is because the upper limit of integration is a variable. So what we're doing here, and I want to look at it in terms of a specific example. Let's look at this function. And I should probably write on here, we'll define this function. Big F of x is equal to the integral from 0 to x of 2t plus 1 with respect to t. Okay? Here's what that means. Let's just plug in different x values and see what happens. In fact, I'm going to make a chart here. So I'm going to say x and big F of x. Go back to your freshman days when you were making function charts and plugging in values and figuring out what the value of the function is at those points. If we put 0 in where x is, say we put a 0 in for x. Okay, now when we do that, we'd put 0 in for x here, but we would also put 0 in for x here. So instead of x, we've got a 0 there. Well, what is the integral from 0 to 0 of anything? 0. All right, so the first thing we know about this function is it has a value of 0 at 0. Okay? Oops, didn't want to do that. Let's put in something more meaningful. Instead of 0, let's try 1. So I'm going to put 1 in where x is here. If I want to take the integral from 0 to 1 of this function, what I'm doing is I'm finding the area of this right here. I didn't draw that real well, but I'm pretty close, I think. That is a trapezoid that has a base of 1, a base of 3, and a height of 1. So what would that area be? 2. That would be 2. So when we put 1 in for x, we get 2. Let's try 2. Oops. So instead of x equals 1, let's put x equals 2 in and see what happens. So we put 2 in. That means we're looking at the trapezoid here. And the height of that trapezoid is going to, or I'm sorry, one base is going to be 5, one base is going to be 1, and that is going to be 2. So what is that going to be? It's going to give us 6. I don't think I need to do a whole lot more here to show you what's going on. We can see that if we put in different x values, we get different areas for this region, right? For this particular example, it's going to be a trapezoid. I do want to show you one more, and I want to show you what happens when we choose a negative. Let's say I'm gonna use 2 negatives. Let's go -1 and -2. -1, we're going to go from 0 to -1, and that's going to be this region right here. Well, we could check it out mathematically, but what do you think is going to happen there? Those are going to cancel out, and that's going to actually give us a 0 there. If we put -2 in there, now we're here. And so what we have is a triangle here that has an area of, well, that triangle is going to have an area of what? Anybody know? It's a height of 1, it has a base of 1/2, so it's going to have an area of 1/4. And then this one is going to have a width of 3/2. It's going to have a height, if we put -2 into this function, it's going to have a height of -3. So that area right there is going to be what? Okay, it's I'm going to just put 9/4 here to start with. Now, the question is this area positive or negative? Jeremy is the only one I heard that got it right so far. Why negative, Jeremy?
Because you're going backwards?
Yeah, we're going backwards. We're starting at 0 as our lower limit and going to the left. So since it's above the x-axis but we're going backwards, that's going to be negative. And this area is going to be positive. Okay, so we have 9/4 minus 1/4 would be dos. Or zwei. So what does this function look like? What does the big f of x look like? Let's graph these and see what happens. We're at 0, we've got 0, 0. We've got 1, 2. We've got 2, 6, which is going to be up here somewhere. We've got -1, 0. And we've got -2, 2. Anybody know what that graph is? It does look like a parabola. Okay, now, here's what the fundamental theorem of calculus is saying. If I take, and I don't know what the equation of this parabola is, although I actually do, and you might in a moment if you think about it. If I take the derivative of this parabola, guess what I'm going to get? Two x plus 1. So the derivative of that parabola is going to be 2x plus 1. So, what'd you say, Joe? Yeah, the antiderivative of this would be x squared plus x, and that is what this parabola is right here. That would be x squared plus x. Okay? You guys remember what antiderivatives are? We'll get into that later. That's actually going to be the second part of the fundamental theorem. So, did a lot of scratch work here, put a lot of stuff together, but essentially what happened, what we just did is we figured out what the function looked like if we put in different values for x into this integral. And then when we took the derivative of that function, we got back to this integrand right here. The integrand is the inside part of the integral. So what we're taking the integral of. Does that make sense? Kinda, sorta. Here's what I really want to do to formalize it. What we're going to be doing with this, and we're not going to do a whole lot more than this with it. If we take the derivative of an integral where the upper bound is a what? Is a variable. So if we take the derivative of an integral where the upper bound is a variable, we essentially get the integrand as our answer. It doesn't matter what the lower bound is, as long as the lower bound is a what? It's a number. It's got to be a constant. As long as the lower bound is a constant, then the derivative of the integral, with the upper bound of the integral being the variable, is just going to be the integrand. So what is this integral, the derivative of the integral, going to be? No.
X squared.
Yes. Now, there's an interesting thing going on here. We have two different variables. Why couldn't I use x here and dx here? Yeah, I'm already using x as the upper limit of the integral. We would have kind of a circular reasoning type thing going here. We can't take the integral with respect to some variable and also use that variable as one of the bounds, because then the bound is changing as the integral or as the area changes, and that doesn't work. So we have to have a different variable of integration than the variable that we use in the bounds. So because of that, when we use x in our upper bound here, we change the variable to t just so we have a different variable. Essentially what we do then to solve a problem like this is we take this x and we plug it in there for t. And we get this. So the derivative of the integral is equal to the integrand. Does that make sense? It seems really simple, and unfortunately it doesn't stay that simple. Guess what we're going to have to use here?
Calculus.
Yes, well, we will have to use calculus. We're going to have to use the chain rule here. Who can tell me why we need to use the chain rule? Cole?
Because the integral.
We're gonna have to use the chain rule here because the upper limit is x squared and not just x. So the fundamental theorem of calculus, the formula that we got, and there's a proof of that formula, had an x up there as the upper bound. When we have something besides just x, but we have a function of x, then we do have to use the chain rule here. And one way to think about it is if we say that x squared is equal to u, so let me do this off to the side here, then we have u equals x squared. The derivative with respect to u of the integral, oops, sorry, I'm writing this wrong, of the integral from 1 to u of t squared minus 1 dt is going to be equal to what? Yes, this is going to be u squared minus 1. However, we want to find the derivative with respect to x. So since we want the derivative with respect to x, that's going to be equal to the derivative with respect to u, sorry, I'm having trouble here, times the derivative of u with respect to x. And if you remember when we did the chain rule, these du's cancel each other out, and then we get d dx. Okay, so we want d du times du dx. Well, d du, the derivative with respect to u we have here, that's u squared minus 1. But then we also have to multiply that by du dx. And what is du dx going to be? We get that from here. And that would not be an acceptable answer, mostly because we introduced this u variable ourselves, and so we don't want that to be a part of our answer. So instead of our u, we need to put x squared back in, so that's going to equal x to the fourth minus 1 times 2x. Now, like most things that I teach you, I tend to do it a longer way first and then show you a shortcut. I don't know if you guys have noticed that or not. You don't have to do all of this work. You don't have to plug in u for x squared and then rewrite it and then figure out what that is and go from there. Let's do this the same way we did the last one, but then use the chain rule to finish it off. So remember, the last problem we did, we took this and we plugged it in for t, right? So let's go ahead and do that. What do we get when we do that? We get x to the fourth minus 1. Now the chain rule part of it, we're going to do the chain rule of the upper limit. The upper limit is going to be our baby here. So we're going to multiply by the derivative of the baby, which is 2x. And hey, look at that. We got the same answer.
Instead of thinking about it like that's the...
What's different about this one? Yes, we have variables in the top and the bottom. And the fundamental theorem of calculus only works when the bottom, the lower limit, is a constant. So what we have to do is we have to rewrite this, and we actually have to rewrite it into two separate integrals, and we have to write those two separate integrals with constants in the lower limit. So we're going to use a property. So this property right here of integrals says that we can, if we want to find the integral from a to b, we can find the integral from a to c, and then integrate from c to b, and add those together, and we'll get this integral here. So what do you think we're going to put in for our c? Our a and b, I think, are obvious. A is going to be x, b is going to be x squared. But what are we going to put in where c is? What'd you say, Evan? I like 0. It really doesn't matter what constant, just any constant. Okay, I like 0 because 0 is easy to work with. Although, regardless of the constant that we use, the constant is not going to come into play at all. But it just needs to be some constant. We could put pi in there. We could put pi to the 17th power in there. We could put e to the pi power in there. It doesn't matter what constant we put in there. It just has to be a constant. E to the pi would be fun, right? Let's just use 0, though. All right, so let's rewrite this. And I'm going to be sure that I write the entire problem here. So this is equal to the derivative with respect to x of the integral from, now the x is going to stay on the bottom, and we're going to put 0 on top, of t squared minus 1 dt plus the integral from 0 to x squared of t squared minus 1 dt. Now, first of all, does anybody have any questions about what I did there? It only partially fixed my problem. It only fixed my problem in this integral, but I still have the problem here. So how do I fix the problem here? Yeah, exactly. So we flip the limits. So we put the x on top, the 0 on the bottom, and we put a negative out front. So it's going to be the opposite of that. So this is going to be equal to the derivative with respect to x of the opposite of the integral from 0 to x dt, t squared minus 1 dt plus the integral from 0 to pi, or 0 to x squared. That didn't change. Okay, so at this point, we have a constant in the lower limit for both integrals, and we have a variable in the upper limit. And remember our rule for derivatives, this goes way back to chapter 3. The derivative of a sum is equal to the sum of the derivatives, so I can take the derivative of this and the derivative of this and do them separately. So to do that, we're going to use the fundamental theorem. The fundamental theorem says that we are going to get, well, what's the derivative here going to be? The derivative, when we put x in for t, what do we get? No. X squared minus 1. But it's the opposite of x squared minus 1 because we have that negative out front. So I'm going to go ahead and put that in there right now. So it's going to be negative x squared plus 1. Is everybody okay with that? And for the second one, this is the chain rule one because the upper limit is a function of x, not just x. So we put that in for the t. And when we put x squared in for t, we get x to the fourth minus 1. But then we have to multiply that by 2x, the derivative of the baby, the derivative of the upper limit in this case. And then it's just a matter of simplifying this here. There's nothing that will combine or simplify. We just need to write it in a more appropriate order. So that would be x to the fourth. Nope, sorry, x to the 2x to the fifth. Minus x squared minus 2x plus 1. I like this one. We're gonna go through this one fairly quickly. We already know what we're gonna have to do. We have a function of x in the bottom and the top, the lower and the upper limit. So we're gonna have to split it up, right? If you guys remember, when we split it up and we put this one up top, the one where we had the lower limit up top was negative. So this is going to equal, like I said, I'm gonna skip through a few steps here, and it's perfectly okay to do this. I'm gonna write the upper limit one first because that's gonna be the one that's positive. And then the lower limit one is going to be the negative one. I'm going to write this down and give you a chance to process it. So then to evaluate this, the derivative of this one, we put cosine of x in for t. And we get what? Okay, we get cosine squared x times the derivative of cosine, which is negative sine of x, minus, we put sine of x in for t here. What do we get? Sine squared of x times cosine of x and then it's just a matter of simplifying. Yes?
For this one, you...
If we take an integral, and the integral gives us a function because one of the limits is a function, and then we take the derivative of that, we get back to the original function. Now, this is obviously not the original function because we had some chain rule stuff going on there. But essentially what we have with some modifications is a t squared function here. And when I say some, I mean kind of a lot in this example because we had a function on the top and the bottom. But what the fundamental theorem is saying is that the derivative and the integral are inverses of each other. Any questions about that?